right? Lots of contributors, and so lots of coordination and resource to be leveraged. And so this afternoon session is going to highlight some of those efforts. And so this is a session entitled Precision Medicine Around the World. So we're going to go ahead and just get launched right into the presentations. These presentations will be 15 minutes in length, and then there will be a 15-minute discussion session, assuming that we all stay on time at the end. So the first presentation is my pleasure to introduce Damian Smedley and to talk about the UK's 100,000 Genomes project.
Okay, good afternoon everyone. So I'm going to talk about the UK 100,000 Genomes project, and this is delivered by an organisation called Genomics England. So you have to look down there. And it's also funded by the UK government. Also, just to say, wearing my academic hat, I'm a PI on the Monarch Initiative and the INPC grants, so you'll hear a lot about how these help the project. And also to say, one of the main reasons I was seconded to Genomics England is because of my involvement with these projects and the fact they realised using phenotype data and using animal models was key to delivering the project. So I'm going to start off introducing the project just sort of briefly, but spend most of the time explaining how we use phenotype data and precision animal models. So just a sort of few numbers. So I was going to do that. Just a few numbers to start off. Obviously, we're sort of sequencing 100,000 whole genomes involving 70,000 affected patients with either rare disease or cancer. And the other 30,000 are obviously the family members for the rare disease cases. So I'm not going to go through all the numbers, but the sort of key thing here is this involves over half the National Healthcare System trusts in England. And the whole of this project is really about transforming a healthcare system. It's not a genomic research project, so this makes things a lot more challenging. And just to sort of give our main goals, obviously the first main goal is to bring benefit to the NHS patients, but we also want to make life easy for the research community and to kickstart a UK genomics industry. Not that there wasn't one at the beginning, but to really make it bigger and to create an ethical and transparent program with broad consent. And this is quite a busy slide, but it kind of helps you sort of realise all the different components you have to put together to build such a system and to sort of transform a healthcare system. So the first stage is for NHS England to contract 13 different genomic medicine centres, and these are sort of dotted all around England, and their role is to recruit the patients, consent the patients, and collect the samples. And then the next phase was getting the biobanking and the sequencing set up. So eventually we sort of came out of a contract with Illumina to perform the sequencing, and a whole new sequencing centre was built in Hinxton on the Genome campus just outside Cambridge. Then all the genome data and all this clinical data ends up in this specially commissioned data centre that's government approved and secure and behind an NHS firewall. And we also try and bring in lots of other electronic health record data on these patients. So this is the real sort of power, bringing together all this sort of clinical data associated with the genome. So there's things like the primary care records, the hospital episodes, and mortality data. And as I said, this is all kind of securely held behind the firewall to keep the patient data safe and kind of make it easier for the public to buy into the program. So to provide access to the research communities and the industry, they come in through this sort of MRC-funded research data infrastructure, so we can provide access to the de-identified data. And this is kind of set up as what we call a reading library, so they can come in, they can install their own software, and they can run their analysis, but they can't take the genomes or the clinical data out. They can only sort of take out a summary of the results. And to sort of summarise the reason we've done this, so we're basically trying to bring the NHS, clinicians, companies and academic researchers all together in one data centre. And this is to make the whole flow from sort of doing research to sort of transforming healthcare for patients a much faster process. So like here on the left is the sort of typical process where a genomics research program gets funded for 5 years, say, the papers come out, and then people start thinking about how to translate this into healthcare, and then maybe a decade later, you see those changes in the healthcare system. So the way we set up Genomics England is we're all kind of in this together in the data center right from the beginning, and it should really speed the process up. So the way we're dealing with the academic research is that they become a member of one of these sort of Genomic England Clinical Interpretation Partnerships, or GCIPs. So there's now about 2,500 academic members of these GCIP domains. And the main point of this slide is to point out it's not just UK-based researchers. Anyone can join one of these research domains and get access to the data. And this is just a list of the domains that have been approved and will have access to the data so far. So you can see this kind of disease-specific rare disease and cancer domains. And then there's these sort of cross-cutting functional domains that cover areas such as electronic health records, machine learning, for instance, stratified medicine. And then there's the industry partners. So at the beginning, we partnered with 13 different sort of pharmaceutical companies and diagnostic companies and SMEs. And they all sort of put a bit of money in to get early access to the data and help us build the system to make it attractive to companies in the future. And then the final bit was obviously with the inward investment from Illuma, they set up a new headquarters just outside Cambridge. There's sort of £50 million worth of investment. So this is sort of part of our aim of sort of kickstarting UK genomics industry. So there's obviously like a lot of new jobs around Cambridge based around this. So I'm not going to talk about cancer today. I'll sort of stick to the rare disease angle that I know more about. And this is a kind of very sort of low detail overview of the overall process. So sort of coming in with the DNA, we get the sequence, we call the variants, we bring in the clinical data, and then we use this multi-pronged approach to interpretation. So the sort of first thing we do internally is we've got a big curation team. So for every recruited disease category, we curate gene panels for these diseases, and then we look for whether any of the variants in that patient's genome are in the applied gene panels. We also run Exome Iser and Genome Iser, so you heard about these yesterday. These are Monarch Initiative products, and Melissa talked about these yesterday, and I'll show you some results from that in a minute. And then we outsource interpretation to these three companies, Congenica, Wuxi Nextcode, and then Amisha have actually rebranded as Fabric now. And then finally, the results all merge together, and then the clinicians and those genomic medicine centers review the results, and then hopefully feed back to the patient, or if they only have research candidates, then they'll interact with these GCIP domain members. And just to give you some of the success stories, so this first one was a 4-year-old girl called Jessica who presented with epilepsy and developmental delay and had all the standard genetic tests. And we eventually diagnosed this de novo deletion in SL2A1, which was causing the GLUT1 deficiency syndrome. And the sort of good news here is there was like a treatment for this. She's been switched to this ketogenic low-carb diet, which has reduced the number of fits she has. And also, being a de novo, it was good news for the parents in terms of having more children. And a very similar case was like Georgia, who presented with developmental delay and all sorts of other problems. And again, we sort of pinned it down to a de novo truncation in a gene, which kind of ended her 4-year diagnostic odyssey. There wasn't any like immediate treatment for this, but like more about that later towards the end of the talk. So now sort of moving into the sort of clinical data collection and how phenotypes fit into this. So this whole sort of treatment cycle involves multiple different steps that we kind of had to almost set up from scratch because they weren't initially prioritized or optimized for genomic medicine. And you can see towards the second half of this circle, this is where the clinical data is really useful in terms of the interpretation and feeding back results and eventual treatment. And we're trying to standardize this as much as possible to lead to this NHS transformation in healthcare. And part of this standardization is to collect the clinical data using ontologies such as the human phenotype ontology you heard about yesterday. So just to show you an example, so we collect the clinical data using the standardized questionnaire, which the clinicians can either access using this Open Clinica system or export from their own like hospital LIMS system. For each recruited disease category, so there's about 200 different disease categories we recruit against, we've defined data models in terms of the HBO terms. So we say, the typical HBO terms for that disease, and the clinician should say whether they have that symptom or not. So we collect that data, and they can obviously add extra HBO terms if the patient's got those phenotypes. So this is just a screenshot showing the sort of open clinical form where they can sort of say yes or no to each phenotype. And one thing I wanted to point out, when we were setting up these data models, we used the MONIC annotation sufficiency score to try and assess whether these data models were really kind of broad and specific enough for the particular disease. So the idea is you can feed this into a MONIC service and get a score for whether it's going to uniquely identify a disease or not. And eventually the clinicians get presented with a summary of their data. And one thing they can do is to sort of choose which gene panels get applied in the analysis. So there's always like one gene panel for the recruited disease, but you can apply extra panels if it looks applicable for that patient. And what we found at the beginning, so initially the internal clinicians in Genomics England were applying these panels, and we started to find quite a few diagnoses were falling outside the gene panels, but there was kind of like an obvious gene panel that should have been applied. So we developed this system that makes use of the phenotype data called Panel Assigner. So this uses the semantic similarity algorithms that Melissa talked about, that Monica developed. And it basically decides, given the patient's HBO terms, what are the best gene panels to apply for that patient. So we're just sort of finishing off, well, we're doing the main program as well, but we're just finishing off the sort of first 5,000 pilot cases and writing this up as a paper. So we collected like some 13,000 positive phenotype annotations for these patients and like 43,000 negative phenotype annotations. There's a 250,000 hospital episodes associated with them. And we're getting a likely diagnostic rate of around 20-25% for these cases, which kind of seems a bit low, but these are patients that have already had all the standardized testing, so it's probably not too surprising. We're also not looking at CMVs yet, so we kind of expect this rate to rise. And this just shows, so you can see this is the number of HBO terms collected for each family, number of cases. You can see, like, unfortunately for most, we've only got between 1 and 5 HBO terms, but they're still quite informative. And then the black bar is the sort of diagnostic proportion, so you can see roughly as you increase the number of HBO terms, you increase the diagnostic rate, and we see a similar trend if we calculate that MONIC annotation sufficiency score for each family. So it's kind of just showing that collecting the data is useful. The more data you collect, the higher the quality of the data, the better. So one of the key reasons for collecting this detailed clinical phenotype data in the project is so we could apply algorithms such as Exome Iser. So looking at those sort of pilot cases, the first 1,000 reports where we've got a likely diagnosis from internal clinical review, and what we find is that running Exome Iser on them, we can get the right variant out of the starting 6 to 8 million in 59% of the cases. And then it's in the top 5 in about 88%. So using this approach of using the phenotype data, we can confirm the variants that were found in the gene panels. We can find extra diagnoses. So this is what the Venn diagram shows. So these are all the likely diagnoses in these cases. And then Exome Iser's got a lot of overlap with the gene panel approach, but it's finding a lot of extra variants. And this is just an example where we found a rare frameshift deletion in the SORD gene for a patient with congenital cataracts, and this gene was not on our panels because there's kind of limited evidence in OMIM for it really being causative, but it was actually highlighted by Amisha when they went through their clinical interpretation team. And they sort of actually got this other algorithm called Fever, which is also another way of doing automated interpretation using the HBO terms. So you can see it kind of ranks it 13th, and they flagged it up as a likely diagnostic candidate. And Exome Iser flagged it up in the top 5 hits due to a mouse hit. So there was a mouse model, an MGI with cataracts. So it was just sort of showing the use of some of the model organism phenotypes. But clearly, like, where the model organisms are going to be most useful is in this sort of realm of research candidates in the undiagnosed cases. So where we've run our standard pipeline, not found a clear-cut answer in a known disease gene, or we've got a missense variant of unknown significance in one of the known genes. So like extrapolating, we're probably going to have like 10 to 15,000 of these cases knocking around by the end of next year where we still don't know what the answer is. So things like Exome Iser and Genome Iser using the model logs and phenotype data that's coming from programs such as IMPC is going to be key to making these new disease gene discoveries. And then obviously we're going to have to interact with the GSIP communities at that point, do transcriptomics for non-coding variants. And what I'm going to end up sort of finishing off the talk is describing how we're going to use precision animal models for some of the functional validation of these variants, and hopefully for testing treatments. So to achieve this, we're sort of interacting with the Genome Editing Mice for Medicine program funded by the MRC, which Steve introduced yesterday. And Sarah Wells, who's in the audience, who knows way more about this, so we can direct questions to her at coffee afterwards maybe. But so the goal here is to sort of leverage some of the sophisticated genome editing tools that have been developed as part of IMPC and at Harwell, to sort of give fast and flexible CRISPR models for the UK genomics community. And the idea is how this runs is there's a peer-reviewed call every 9 months. And just to show you some of the numbers, they've got about 90 applicants in each call. Harwell screens these for feasibility, and then they get sent out for peer review by experts, and like about 20 in each call get approved to actually have the mice made. And these are also made available to other researchers once they've been sent out to the original requester. And just to highlight how, so in the second call we sort of submitted some Genomics England applications, so we're making use of this program now for precision animal models. And the way we sort of selected the initial list of variants that might be of interest was to look at all the negative reports, but look at ones that had variants in gene panel genes. So these might be sort of missense variants of unknown significance in a known disease gene. And then de novo variants outside the gene panels that were applied, and then high-scoring Exome Iser hits. And then there was a whole lot of sort of targeted discussion with members of the genomic medicine centres and the GSIPs to sort of further select these variants down to some of the applications. Yeah, and as I said, there was about sort of 20 selected for each call, and about 12-point mutations selected, and the whole range of diseases, as you can see, intellectual disability, CMT, epilepsy, and the first mice are sort of being produced as we speak, and hopefully we'll have some exciting results next time we talk. So just to reiterate, so these opportunities, this is a bit UK-centric, but it applies internationally still. So yeah, if you've got a particular null allele that you're interested in, it's worth going to the IMPC, seeing if the mouse line has already been made and phenotyped, in which case you can order that mouse, or you can request an IMPC line to be prioritised. And similarly for point mutations, if you're in the UK, there's the GEM program where you can request a mouse, and the US, there's sort of similar initiatives being set up, and I'm sure Kent is going to speak to that at the end of the meeting. So, this is just a sort of quick reminder slide for me. So I stole one of Melissa's slides that, just to sort of say we're trying to engage with the international community at Genomics England by participating in Matchmaker Exchange. So we're looking into deploying the Matchbox solution that's been developed by Monarch and the Broad Institute. We're also participating as a driver project in the Global Alliance, along with Monarch Initiative, to try and develop standards in this area, work with other people. And then, so this is the conclusion slide, so just to put up the sort of main aims, but just to sort of state, so the project's going to end at the end of next year, so we'll have finished 100,000 genomes and reported on as many as possible by then. Research will keep on going on the negative cases. But the key thing that's happening next year is Genomics England will carry on, and it's going into this full commission phase in our national healthcare system. So any rare disease patient that comes to see a clinician, they can, if they decide it needs a genetic test, the default's going to be whole genome sequencing, and everything will flow through the systems we built. And I hope I've managed to convey that, right from the beginning, we've kind of realised that some clinical and model organism phenotypes and precision animal models are kind of key to us delivering the aims and objectives of sort of achieving new diagnoses and opportunities for patients and therapies. And with that, I'm kind of well over time, and I'll finish. I've got the usual acknowledgement slide that you can't fit everyone on. Thanks,
Damian.